Okay, so welcome everyone to the second day of the AGI 20 conference. And here is the tutorial that we are providing with Evgenii Vityaev. We are going to talk on logic and probability synthesis in artificial general intelligence. And specifically, we will be presenting what we call task-driven approach as a logical probabilistic AGI. Most of work that will be presented today is based on works of Evgenii Vityaev and his colleagues. So I'm here mostly to present the work itself, and plus I have made some presentation suggestions and ideas to this work, and also I'm using many concept level suggestions and ideas in my own work that I presented yesterday in the agents project. But here we are going to talk about fundamental ideas of the task-driven approach as a logical probabilistic AGI. So let's start with discussing some problems that are known to the modern artificial general intelligence technology mainstream. And we all know that the mainstream of the artificial intelligence technology is about deep learning. And most of us probably know that there are a bunch of problems connected with applications of deep learning. So let's start with a quick overview of them. First of all, the neural networks are actually providing black box based solutions. So you can make predictions, you can make discernments, you can make some recognitions, but you can't understand the reasons why these predictions and recognitions are made. And in many applications which are critical in respect to error and the cost of error and the cost of training, this just may be not applicable, like military applications, security applications, Medicare, or some domains where the explainability or interpretability of the knowledge models and solutions are required just by legal reasons. Secondly, the deep neural networks are still not showing any reasonable ability for generalization. For example, if you train a neural network to recognize elephants and whales in their natural conditions, you may find that if a whale is washed ashore and you try to recognize a whale on ashore, you will recognize an elephant, and the elephant swimming and surfing in the water will be recognized as a whale. So we need to find a solution which actually understand the semantics of the items presented in the video or in the audio or in any data that we are going to process with artificial intelligence solutions. So the recognition is general enough and meaningful and based on the structured inner properties and features of the objects being recognized, rather than just distributed representation of features specific to given training set. Finally, our third item is that neural networks actually memorize specific patterns that may be randomly representing different target images in the training set, and the features that may be selected based on this training set may be just some random items like specific pixels, and there are known attacks on the neural networks, like you can replace a single pixel in an image and have error in your recognition, or you replace the image with noise and the still system can recognize this apparent noise as something reasonable. And finally, the neural networks are not invariant with respect to permissible scale transformations. Like if you train the neural networks on small mice and large animals, and then you try to recognize large mice and small elephants, you will have mice and animals probably mess it up because of the scale change. So alternative approaches that are trying to solve some one or another or all the issues that we are talking about are explainable artificial intelligence or interpretable artificial intelligence, agent-based approach, AGI, and the task-driven approach that we are going present at this work actually another way to look at the problem and to tackle the problem. Okay, why it's not switching? So let's go have a quick review of the other approaches, because on the later discussion we will see how the task-driven approach is actually taking the best things from any of these approaches that we are overviewing right now. So the explainable artificial intelligence is trying to just take a neural network model and explain why the neural network is or the deep machine learning model makes certain decisions. So you may just be trying to show contribution of each of the feature forecasting the given the predictions that neural network or machine learning model is making. There are also, you may be trying to find the influences of individual characteristics that are forecasting this or another output. And if you actually do that, then many samples are showing that these characteristics or features contributing to specific decisions made by neural networks are actually apparently random. Like on the right, you see the explanation of the cat recognized on the image, and the green dots are representing the pixels that were most contributing to the decision of the neural network recognizing the cat. And you will find that these particular pixels have nothing to do about the cat. They just have about some special patterns that happen to occur with cats given training set. And still, you have they have nothing about paws, they have nothing about ears, they have nothing about eyes, just some random features. And instead, we are going to see if we can actually figure out the real features of the objects that we are trying to recognize. And so the recognition is based on these semantically meaningful features rather than on randomly selected features. Another approach is agent-based approach, and it's developed mostly in works on Stuart Russell and Peter Norvig, and it treats the development of artificial intelligence from perspective of some rational agent interacting with the environment. And then there may be a scenario where agent performs reflections in respect to the environment. It's may have some goals. It may perform some reinforcement learning interacting with this environment. And then in the course of this reinforcement and the learning, agent increasingly acquires the skills required to operate within this environment. Then the artificial general intelligence is based on different complementary definitions, like Ben Goertzer's definition makes focus on ability to achieve complex goals and complex environments. Shen Leg and Marcus Hatter are making it more specific that environments may be different, that there might be a wide range of environments. So it shouldn't be just complex environment or with a complex goals being reached, but the agent may be actually or the artificial intelligence system may move from one environment to another and still be able to operate within this environment. Then P1 is making it even more specific that a system should also be able to deal with insufficient knowledge and resources. So it's not just enough to reach the goals eventually. The system should be able to reach the goal timely enough so the goal keeps reaching the goal keeps meaningful, because if time if it spends enormous amount of time to reach the goal, that there is no point to reach this goal, because there may be just not enough resources to fulfill the action. So in this work, in context of the further presentation, we will try to synthesize the definition of the artificial general intelligence as ability to solve cognitive tasks as a whole, acting purposefully, adapting to environment conditions through training, minimizing risks, and optimizing losses to achieve their goals. So here we are coming down to the task-driven approach. And this approach is actually, as we will see later, it quite complementary in respect to the previous approaches. However, it has been developed from the grounds of fundamental mathematical works started more than 30 years ago. It has started with works made by Samokhvalov, where he tries to identify the task. So the task is assumed to be defined or comprehended if and only if we have a criterion for solving the task, a criterion for checking whether the presented solution is really a solution for a task. In mathematical theories, such a criterion is usually considered to be proof of the task solution. So if there is no way to prove the task solution, then there is just no task. There is just some vague idea that we don't know whether we reach this, whether we follow this idea or not. And this criterion of the task solution is applied only when, within the framework of the formal system itself, we have both proof of the task solution and the ability to verify the solution by means of the system itself. This proof is indeed a solution to the task. So from the perspective of the agent-based approach, the agent can actually reach the goal or complete the task if it has its own means to verify that this achievement is really done, so the task is really achieved. And mathematically, it has been proved that only in weak formal systems for which Gödel's theorem doesn't hold, we can determine only in such weak formal systems we can determine that whether a particular text or particular solution is a proof of task or not. As a result, Hilbert's program for substantiating mathematics is formulated differently. It is not necessary for all mathematics to prove its consistency. This is impossible and unnecessary. It is possible to formulate and solve problems within the framework of weak formal systems. And here we are coming right to the idea suggested by Ben Goertzel on the AGI 2019 conference last year. So what Ben suggested is let's start talking about so-called narrow artificial general intelligence. So let's go back to the definition of the complex environments, complex goals, limited resources, and so forth. So let's imagine we have infinitely complex environment, infinitely complex goal, infinitely limited resources, and everything is infinitely complex. And then if we create an imaginary system which can still operate with this infinitely complex situation, then we have infinitely general artificial intelligence, which is not achievable. We can never create completely infinitely general artificial intelligence. On the other hand, if the environment is not complex at all and the goal is extremely simple, then we have just narrow artificial intelligence. But then let's find ourselves in between. In between, we have moderately complex environments, moderately complex goals, somewhat complex, somewhat limited resources, and that gives us narrow general artificial intelligence. So it's still somewhat complex, and we deal with somewhat complex goals, somewhat complex environments. So it still needs to be general enough so it can operate in few different environments, but it can't solve problems in any imaginary environments in the universe. So then the narrowness of the artificial general intelligence can be defined in terms of complexity of the environments and goals and resources definition. So what we can actually do, we can find a way to somehow describe the environments, the goals, the resources, and within this description, try to solve the problem of the artificial general intelligence capable to operate in such formal system. Now, let's consider the notion of task from the perspective of cognitive sciences. In cognitive sciences, generalization of the task concept is the concept of the goal. A goal cannot be achieved without of criteria for its achievement. Otherwise, we can just always assume that it has already been achieved. Therefore, the formulation of the goal should always be accompanied by a definition of the criteria of the goal achievement. And reaching the goal gives a certain result. The only psychological theory in which the goal achievement and the result obtained is considered as the solution by the brain of the task to satisfy some needs is the theory of functional systems by Anokhin. This theory also reveals the psychological mechanisms for achieving the goal and solving the task by the brain. Perhaps, as Anokhin says, one of the most dramatic moments in the history of the brain study as an integrative formation is the fixation of attention on the action itself and not on its results. We can assume that the result of the grasping reflex will not be grabbing as an action, but that totally afferent stimuli which corresponds to the signs of the captured object. The totality of afferent stimuli is the criterion for achieving the goal in TFS, or theory of functional systems. That means when we are trying to switch the light in the room, the succession of the goal achievement, success of the goal achievement is combination of our finger feeling the switch, the click sound of the switch being turned is changing position, and the light flashing in front of our eyes immediately when the click is happening. So when we pull our finger to the switch, we expect everything to happen. And if the light is lighting up in response to our finger pointing to a switch and pressing on it, and with the following click, then we are getting the emotional feedback that we have succeeded the task of the switching the light on. Therefore, a prerequisite for the purposeful behavior of an intelligent agent is goal setting, including a criterion for achieving the goal. And this thesis, as well as other theses that will be presented in the course of the work, are all described in greater details in the publications that will be rendered displayed at the bottoms of the slides for the reference. So, the definition of the goal is paradoxical, since the criterion of the goal achievement doesn't contain any knowledge on how to achieve it. So from the beginning, when we start interacting in some environment, we don't have a knowledge how to achieve a goal. However, we still can try and fail and succeed incrementally interacting with the environment. But still, you can define a goal without of determining how to achieve it. Because we can have different ways to achieve the goal, but there is only one way to confirm that the goal is achieved. There is only one goal: to have the light turned on. We can switch the light on with finger, or we can just take we can take a cup and throw the cup into the switch, and the light will be turned on. Or we can ask someone in the room to switch the light on, to press the finger on the switch. So there may be different ways to solve the goal, but there is only one criteria that the goal is solved with the light. So the paradox of the goal is called the goal paradox. As it follows from theory of functional systems, the brain with purposeful behavior constantly resolves the goal paradox, determining what, how, and when to achieve this or another goal. What are the goals in TFS? Every need, when even with a slight deviation of the vital function from the optimal level for metabolism in human body, in which the need manifests itself, is immediately perceived by special receptor apparatuses, forming the criterion for the goal achievement. Thus, the need is the goal that is set before the body. So the mind is trying to achieve this goal in order to satisfy the needs of the body. Interaction of results and goals in the theory of functional systems is carried out in several ways. According to the dominant principle, hierarchy of results, and the result models or models of the results. And these are three principles which are actually all essential parts of the whole design that we will be discussing further during this talk. So leading excitation determining a focused activity is motivational excitation, which is formed on the basis of the dominant need, which is dominating in the living organism or artificial system at given moment of time. Then, in relation to the dominant functional system, the remaining functional systems or subsystems are arranged in a hierarchy according to the principle of hierarchy of results. So in order to switch the light, first I need to direct my finger towards the switch. Then I need to keep pulling my finger towards the switch. Then I need to start feeling the the switch under my finger. Then I need to apply more pressure to the switch. And then I need to hear the click. And voila, then I have the light on. So, for example, a hungry rabbit is dominated by a functional system whose activity is aimed at finding food. At this time, other functional systems that determine blood pressure, respiration, exertion are aimed at better providing the dominant food-producing functional system. According to Anokhin, the central mechanisms of functional systems that provide purposeful behavior all have the same architecture. Afferent synthesis. The initial stage of a behavioral act of any complexity is afferent synthesis, which includes the synthesis of motivational excitation, memory, situational, and triggering afferentation. Motivational excitation. The goal setting is carried out by the arising need, which is transformed into motivational excitation. Memory. Motivational excitation, on the basis of the existing experience, extracts from the memory the various sequences of actions that can lead to the goal given the previous experiences of an agent or an organism. Furnishing afferentation. Only those methods of the goal achievement are extracted from the memory that are applicable to the given situation. For example, if we want to switch the light on in a room when we don't have switches, probably we should call the phone, should call the room service, or we need to go to internet and find some intranet site where the switches can be used, virtual switches can be turned, so the light is going on in the room with no physical switches. Then further starting the fermentation. How and when we start the actual execution of the flow of action. Starting the fermentation is also a situational fermentation, only related to the time and place of achieving the results. Starting a fermentation answers the question of where and when the result can be achieved. For another example of the hungry rabbit, if the rabbit is going to start searching for food, and then there is a tiger appearing in front of the rabbit, then that's probably not a good place for start fermentation in respect to food searching, cognitive or functional schema. It's better it's starting the fermentation to running away from the tiger. Thus, at the stage of afferent synthesis, the goal paradox is largely resolved, and it is determined what, how, and when to do achieve the goal. Then there is a decision-making process. At the afferent synthesis stage, several ways to achieve the goal can be extracted from the memory by motivational excitation. Like rabbit can use one way or another way to search for food, or it can use one path or another path to run away from the tiger. At the decision-making stage, one program or one way is selected, or one hierarchy of subsystems to be executed is selected, and that's hierarchy of action represents a particular action plan. A particular action plan also draws from memory the entire sequence of actions related to goal achievement, transforming the goal into particular goal, determines the way its achievement. It's called, in the TFS, supreme motivation. So let's consider the visual example of that. So in the very beginning, we have what is called a goal, or super goal in this example, because it is supported by hierarchy of sub-goals. And the goal is defined together with criteria of the goal achievement. So the blue are the properties of the situation or features of the situational context that are expected to be specific to the situation when the goal is achieved. And the red part are the our afferentational capabilities that let us actually feel the properties of the environment at the moment of the goal. Like if we taste pleasant feelings, if we taste sweet carrot, like if we are a rabbit and we feel sweet carrot in our mouth, then likely we have grasped the carrot. If we have a light in front of our eyes, then we probably have reached the switch in the room, so we were able to turn the light on. And each of the goals can have sub-goals, and each of these sub-goals, like running towards the carrot for rabbit or pulling the finger towards the switch, or each of them can have their own criteria for the goal achievement. A particular action plan extracts from memory the entire sequence and hierarchy of results that must be obtained when implementing and executing the action plan. In TFS, this sequence and hierarchy is called the action result acceptor, which is the criterion for achieving a particular goal. The acceptor of the action results represents the dominant need or a goal of entire body transformed into the form of advancing brain excitation into a kind of a complex receptor of the future reinforcement. Thus, the acceptor of the action results is a criterion for a criterion for achieving a particular goal. Then the reinforcement is the sanctioning stage. A purposeful behavioral act ends with the last authorizing stage. At this stage, under the action of a stimulus that satisfies the leading need or reinforcement, the parameters of the achieved results cause reverse afferent flows, which in all its properties correspond to the previously programmed properties of a reinforcement stimulus in the acceptor of the action results. Implementing particular action plan is reinforced and recorded in the memory in case if this sanctioning is worked as expected. Effector mechanisms of the functional systems. Evaluation of the achieved results of an action occurs with the help of an active orientation research activity, which occurs in all cases when the result of a perfect action does not correspond to the properties of the acceptor of the action result. That is when a mismatch occurs in behavioral activity. So if we don't know the action plan of for particular goal, and our expectations are not met or are not matched when we complete the sequence of the actions according to the hypothetical plan that we created, or if we are working in some novel environment where the rules of the game are changed, and what worked for us in the previous environment is not working in the current environment, then like, for example, instead of the light switch, there could be just a button for the for some doorbell, and we just hear a musical sound or bell ringing instead of the light going on. It was just a bell button, but not a light switch. So when a mismatch occurs during behavioral activity, then we need a way to actually update and rebuild our behavioral schema. Thanks to the inclusion of such reaction, Afferent Synthesis is immediately rebuilt. A new decision is made, a new particular action plan is being built. In this way, the brain solves tasks to satisfy all its needs, according to Anton. What is the task in general case? Let's have some more specific definition of the task according to the mathematical works of our colleagues in Novosibirsk. So the task is defined only if there are few things. First, there is an indication of the subject domain to which the task belongs. Knowledge about the subject domain recorded in the form of its model, including a description of the signature and structure of the domain description language, a set of terms and concepts like ontology, initial data, facts, and knowledge written in terms of ontology. I need to make some clarification here. As soon as we have mentioned words like language and ontology, on one hand, involving language and ontology are important because we are talking about interpretable and explainable solution, and because further we will be talking about semantic inference. But when we are talking about semantics and ontology and language, here we are talking not from a perspective of semantic web or RDF or OL ontologies or particular entity relationship models or object-oriented design of the knowledge base. So that's not about the knowledge engineering language or knowledge engineering ontology. That's here we are talking from the mathematical perspective. So, for example, if we are talking about animal operating in a maze, then the ontology of the animal is about the holes, walls, grass, pieces of food lying here and there, actions that animal can make in this environment, like changing the order of feet movements so it can crawl over the hole, or movements of the teeth, like opening the mouth and closing the mouth when grasping the foods. So these concepts within ontology are specific actions that animal or agent can make, and the description language is formal mathematical definition of the all possible set of the actions. And of course, in this the ontology and can be hierarchical, so it can be not a plain graph, it may be hypergraph, like any complex action may be decomposed into more atomic actions, and any atomic action may be also further decomposed into less atomic, even more atomic actions. They don't necessarily have some labels or words associating them with specific ontological terms, and the relationships like either or property of or similar to, but still they are defined as corresponding to particular properties of the environment. Further, besides having the subject domain identified and the knowledge about subject domain, it should be possible for every task that we are experienced with to specify what is the request formulated in the task to the subject domain should we get an answer. So what we are going to do? Either we need to satisfy either whether we are hungry and we need to fill our stomach, so we stop feeling hungriness, or we need to mate with a partner to breed to make the offspring to keep our to keep our children living. So we need to specify which particular goal we are trying to solve and what is the request actually sponsoring or motivating the goal or a task. Then there is a criterion for satisfying the request is defined. So it is determined in which case it can be considered that the response to the request has been received. Like, okay, so the light is on, the taste of carrot is in the mouth. So that's the criterion for satisfying the request. In what context should we look for the answer to the request? What do we expect from the result, and what are its consequences to what to do if the answer is negative? So like when we should be able to start executing the tasks, and what can we do if we are not able to complete the task. In the task approach, the purpose of artificial intelligence is just automation of the process of task solving. So if we can define the task, if we have the environment, then given the ontology defined mathematically, then the AI is just about automation of the task solving within this environment, understanding the automation as formulation of the requests and solutions in terms of executable specifications. And these executable specifications could be just completely based on the ontology describing the model of the environment and this domain description language covering this ontology. Mathematically, this has been developed in the works of Yershov, Goncharov, Sviridenko, and Vityaev as sigma definability of computations, a model based on the truth of sigma formulas on a constructive model M and this least superstructure HW of M. That's something which sounds nice. We can't go in details of it. There are lots of references, and that's quite solid mathematical foundation, but we'll be not talking about details of it. We'll be talking about higher level implications of using this. Then automation of task solving is termed in terms of what is called semantic modeling. And task definition in semantic modeling is as following. It is assumed that we have a multi-sorted constructive model M together with its least superstructure HW of M, which is kind of basic computer. And then the task domain model under consideration of that is formulated in the signature of the predicate calculus language of the basic constructive model M together with its least superstructure, a set of sigma definitions, sigma formulas and sigma terms of this language. Moreover, recursive schemes of sigma definitions are allowed with more restrictions on the occurrence of definable predicates and terms in them. A query to a domain model is also defined as a sigma formula in which both signature constructions of the constructive model M and defined predicates and terms of the domain can be used. Then, by the solution of the task, we mean a set of constants that make the sigma query formula when its variables are designated by constants true on the domain model. The truth of the sigma query formula is the criterion for the task solution. There may be, in specific cases, there may be several solutions or set of constants that make the sigma query formula true. And then it is possible to choose the best solution, taking into account the context of the problem, like time that we need to solve the problem or resources that we need to consume to solve the problem, or extent to which the problem may be solved, based on the specific context described in terms of the same model. Further, we show that the formalization of functional systems can be defined as a special case of the definition of a task. So the brain, for instance, with all its physiological mechanisms, provides a solution of its task of the needs satisfaction in purposeful behavior in this sense. In semantic modeling, the task solved by the brain, is in the following way. The domain model is an experience that is obtained as a result of training in which purposeful behavior is carried out. So that's important. So when we are talking about the domain model, it can be thought as a belief of the world on the side of the agent performing experiential learning itself. So the domain model is not the model of the world which is created by the external observer. So the domain model is completely experiential, and that can be thought as a completely subjective model of the outer world created by the inner cognitive schema of an agent interacting within the environment. So when we are talking about the language and when we are talking about ontology, it's all about internal agents' experience, past experiences and conclusions and rules and inferences based on these experiences. And of course, if this model is correctly describing the outer world, then the agent can perform in this world in a way so it can compete with the other agents. But if the model created by agent's inner cognitive schema is wrong, then the agent unfortunately will die or will not perform as well as its competitors in the environment. Well, besides the domain model, we need to define the request, and the request or a goal marked blue on this picture is a need that must be satisfied in specific case. And let's denote the request or a need as predicate P0. Decision making is carried out by choosing particular action plan based on experience and model of the external world, leading to an object as such an object so that P0 at A. A particular action plan converts the goal request into particular request given a way to find the desired object, and together with the totality of the goal sub-requests and the hierarchy of corresponding results. An action, and so the action result acceptor is built in respect to the complete behavioral schema. The result of the task solution is the object, the situation or a context perceived by the set of afferent stimuli. That's a red block on which the predicate P0 is true, so the need is satisfied, and that is criteria for the task solution. Here is the actual Anochen's schema, which can help us to figure out the role for causation in this design. So Anochen, so if we look at this scheme, everything starts with motivation, and motivation is the black triangle. And let's consider again, we are trying to switch the light in the room. And we are in the darkness and we need more light. So our inner motivation is to have a little bit more life in our life. So we start an action by pulling the finger, and that's the white triangle in the middle of the schema, and that's pulling the finger toward the switch starts our action in the outer contour, our contour in the outer environment. And when at the same time, when we start pulling the finger, we send the signal through our inner contour to the input, where we start expecting some results from our action pulling the finger towards the switch. And when we recognize, for example, when we see that our finger is approaching the switch, we are already getting some positive feedback because some partial schema is being completed. We see that we are succeeding in pulling the finger towards the switch. But still, the overall schema acceptor is not working because we are still in the darkness. We just barely see our finger pointing towards the switch. So then the triangle on a second from the top white triangle is having another arrow which lets us continue the action. So there is no, the action is not completed. We are going towards the another efferent stimuli that makes us continue the action, and that's the second white triangle on the bottom on the right. So we keep applying the strength to keeping the finger pulling towards the switch, and finally we have reached the switch and we have clicked, and then there is very top white triangle where two signals are facing each other. One signal is our expectations sent through the inner contour, and other signal is about the click sound and the light in our eyes, and then the information is coming to the result acceptor result triangle, which is saying that our action is completed, and it sends inhibitory signal to the motivation triangle, which is black one. So the motivation is actually not should be suppressed from this point because our goal is achieved. And then according to Anochen, we have the principle of advancing reflection of reality. So when we start doing something, we actually expect that something will change in our environment because of our action. As Anton said, there was one universal regularity in the adaptation of organisms to external conditions, which subsequently developed rapidly throughout the evolution of the living world. A highly rapid reflection of slowly unfolding events in the external world. From this point of view, we not only make a decision and choose an action plan for any decision, but we always predict the achievement of the goal, an acceptor of action result. If we are talking about the human brain, then we are talking specifically about collateral branches of the pyramidal tract, leading to many neurons copying the efferent premises that go to the pyramidal tract, according to Anton. And now we are getting right to the topic of prediction. And interestingly, then prediction can be also thought as explanation. So if we are trying to build the chain of actions and responses to these actions accordingly to some future, like there is a goal and we're trying to build the path towards the goal and we are predicting outcomes on each path on this way to the goal in the future, then we are trying to make the prediction. However, besides the predictions, we can also explain something which is already happening. Like we can have some historical data and we might want to apply some data mining or knowledge discovery in respect to that existing volumes of data, and we want to find the causal chains in this data. So when we are finding the causal chains in the historical data, we are effectively doing the explanation of the causal or temporal or spatial relationships between the different items in our memory. So effectively, the prediction and explanation may be explained in the same terms that we are talking about now. And then just two use cases may be applied, like explanation is about finding the laws in the past, and prediction is using the laws found in the past in order to predict the future, to be more successful in the future based on our past experiences. And when we are talking about the prediction or explanation, we can implement two different approaches, like deductive nomological, facts and laws based explanation, or inductive statistical explanation based on facts and probabilistic laws. So the idea is the same in both cases. In the second case, we are just dealing with probabilities. And in probabilities, everything is probabilistic. So we have probabilities. So all the facts have specific probabilities. The laws derived from these facts are having probabilities, and we derive some predictions or conclusions or explanations. They are all probabilistic as well. To search, in order to search for the result and solutions in semantic modeling, we may use probabilistic laws, and that's what we're actually suggesting to do in the further discussion. And in this case, simultaneously with inferential and prediction, we are making the forecast of the result achievement. So in the end of the inference chain, we can forecast whether we achieve the goal or not. And of course, if we are considering different alternative paths to the goal, then if some of the paths having better probability of better forecasted probabilities so that the result will be achieved, that's the path that we are going to actually take. The search for the result and task solutions in semantic modeling can also be carried out by some search in the constants of the model, which corresponds to the trial and error method in purposeful behavior. And there are a few problems that are generally inherent to the statistical inference and to inference and any inference. The first, there is a problem of statistical ambiguities. Statements obtained in the inductive inference may infer contradictory statement. For example, like here, if we have Streptococcus disease, and there is one rule that almost all cases of the disease are quickly cured by penicillin, and there is another law that almost always the penicillin-resistant streptococcal infection does not occur with penicillin, and both of the rules may have some supporting evidence by different combinations of facts, and the rule L1 is supported by C1, C2, and the rule C2, the rule L2 is supported by C2 and C3. But if we experience a case with both of the facts C1, C2, and C3, then these rules L1 and L2 are incompatible. So the rule L1 says one thing, rule L2 says another thing. So L2 predicts that the patient with C1, C2, and C3 observations will be cured. Rule L2 says the patient will not be cured. So the doctor using this inference is in difficult situation. So the solution to the problem is resolution of that fact that these two rules are not specific enough. These two rules are too generic. And in order to solve the problem, we need to have more specific rule, either to create a more specific rule L3, which would state that what happens when the penicillin-resistant streptococcal infection is an exception to the rule L1, or we create a more specific version of rule 1, saying that the almost all cases of disease are quickly cured, except the penicillin-resistant ones. Or we create rule 3, more high-level rule 3, which will be about saying that based on whether the infection is penicillin-resistant or not, we need to apply rule L2 and L1. So that's more about logical design of the solution. But that way or another, we need more specific rule covering the given medical case. Mathematically, to eliminate conflicting inferences, Carl Hempel introduced the maximum specificity requirement, or MSR. And we can improve the quality of our predictions using more specific rules, and the rules should be specific enough to cover given data or given context within the given domain model. And another problem of probabilistic inference is about decay of the probabilities. So if we are doing chained inferences, then there is a known problem that probabilities or decay down to 0, and eventually, if we have a long inference chains, there may be all predictions may be close to 0, and we won't be able to rely on this prediction. So how we do the prediction inference in logic programming? So if we consider the prediction as a request G to a program for given multiple rules and applying to our subject domain and facts that we need to make prediction for, then we can build the trees based on these rules, and these trees may be leading us from the goal towards the original terms that can be used to backchain and provide the prediction in respect to whether the goal is achievable using these facts or not. From the point of view of semantic modeling, let's consider the model theoretical semantics of logical programs where the facts are statements of the empirical system representing the domain model. In this case, the process of inference of prediction can be generalized by considering the inference as a calculation of the truth of the predicted fact G, consistent of the discovery of facts C1, Cn of that empirical system, from the truth of which the truth of the predicted statement is calculated according to the laws L1, Lm, that are the laws that we have learned so far. And then together with the inference of the fact G, we can do assessment of the truth. With this view on the inference, it can be generalized, defining new relationships between statements and models. We can consider the inference not only as a verification of the truth on the model, but also as a search for facts in the model that are predicted with maximum probability the interested statement, or as a search for the most probable or specific. And such inference is called by us as semantic inference, and we will be talking about it later. Inductive inference of the theory and knowledge in the subject domain. So if we consider the main model, DM is represented by an empirical system, then the domain model theory is set of all universal formula that are true on this empirical system. It is known that this can be represented as a set of all rules that are true in the following form, and maybe a rule C, which is subrule of the another rule given the specific condition. And the law specifying this condition is that C is true on this empirical system. The premise of the rule is not always false on it, and each subrule of the rule C falls on this empirical system. And then L is the set of all laws on this empirical system. And then there is a theorem that a probabilistic law on the empirical system is a rule C whose conditional probability is strictly greater than the conditional probabilities of all of its subrules. So what we need to do during the inference, we actually need find for laws which are built upon subrules, and whenever the probability of the law of the top three of the root of the tree that we are building from subrules is increasing, then that means we are going in the right direction, and we are increasing the probability of our compound rule. And then the strongest probabilistic law is called the probabilistic law, which is not under the rule of another probabilistic law. So if we can't increase the probability for a given set of rules applicable to certain context and given a number of facts, then that's the strongest probabilistic law that we can apply given the context. And then the LP is the set of all probability laws on this subject domain or empirical system, and then the specific law is subset of all these probabilities laws, and then we can call this set of probability laws is a theory or domain knowledge about specific environment or specific empirical system. All that said, we can assume that semantic probabilistic inference is the solution for a statistical ambiguity problem. So we can build semantic probabilistic inference as a sequence of building the probabilistic laws, finding the strongest probabilistic law. And the strongest probabilistic inference goal is to strictly increase the likelihood of rules in the inference process, in contrast to predictions in logical programming. By the maximum specific rule of the or inference of the atom G, we mean the strongest probabilistic rule, strongest probabilistic law, or a rule of the inference tree G having the maximum value of the conditional probability. And then there is a theorem that, or a solution of the statistical ambiguity problem, that the inference that use only maximum specific rules is consistent. And then the domain knowledge consists of the following. So first of all, there is a volume of all rules, then and that's LP, so that's the domain knowledge. Then some of these rules may be maximum specific rules or MSRs, and some of them may be just specific rules that just provide probability equal to 1, and they may not need probabilistic inference. Given this design, we can come down to semantical modeling of the elements of the human or animal intelligent behavior, or elements of the intelligent behavior of the simple artificial intelligence agents. So let's start from the formal model of a neuron, which can be thought as an atomic element, the most atomic element of any cognitive schema in biological world. And the goal of a neuron, in the simplest case, is to provide the action acception result. So if G denotes a stimulus on which the neuron responds unconditionally, then the stimuli arriving at the dendrites can establish conditional connections with the excitation of the neuron G. And new stimulus are added to the rule only if they increase its conditional probability in this design. This is a manifestation of the conditional connections closure at the level of a single neuron and its plasticity. Neurons respond faster to the most probable conditional connections, and hence first of all on maximum specific rules. And we will further show some demo how the model based on such mathematical model of a neuron is can be applied to operate the behavior of the artificial animals in virtual environments. Of course, you can, that's just description of the application of this semantic probabilistic inference used to build the simplest atomic model of the cognitive design, a neuron. If you build a network of neurons, then you can get in just to another level of complexity. So you can just build probabilistic inference based on the neurons, while the single neuron will still be operating within the scope of the same design at the lower level of the schema. So neurons operate with, and by the way, the fact that a lot of decision-making power is focused in dendrites rather and forks of the dendrites and graphs and subgraphs of the dendrite connections has been published last year in few publications. Which actually gives us idea that we underestimate the capacity and performance of the human brains, reducing them just to neuron-based networks. Now, how the action result acception can be used and can be implicit to the learning and to memorization of the successive actions. Let's talk about emotion switching function. Semantic probabilistic inference formalizes the concepts of probabilistic forecasting and probability, which is introduced in the works of Feigenberg and the information theory of emotions by Simonov. Summing up the results of our own experiments and literature data, we came to the conclusion that emotion is a reflection by the brain of humans and animals of any actual need, its quality and magnitude, and the likelihood of satisfying it. And that's quickly quite complementary to the theory of functional systems, where decision-making is carried out by choosing one specific action plan, taking into account the probability of this forecast and emerging emotions, which is an important addition of the information theory of emotions to the theory of functional systems. In this addition, emotions are a necessary criterion for choosing between different ways of achieving a goal, taking into account the probability of achieving the goal, complexity, laboriousness, as well as authorizing differentiations when need is satisfied. Therefore, decision-making and the choice of a specific way to achieve the goal is carried out by switching from function of emotions. In artificial intelligence for intelligent systems, such criterion is called utility. In mathematics, it is studied, so there is another reference, but let's move on to the actual illustration of how the emotion switching function works. So from the left to the right, we see the temporal axis, so the time goes from left to right, and the living organism fulfilling some need or reaching some goal, or artificial agent trying to achieve some goal or task posed by humans, is going through different cycles, and these cycles are Efferent synthesis and decision making: what to do, when to do, how to do, and in what is the particular way of doing that. And then another stage is acceptance of the action results. So when we start and all the way from left to right, these cycles are supported with the afferentation from the outer world. And when we when we start the execution of this, everything starts with some motivation on the right at the top, and this motivation request for achievement of goals or a combination of goals is starting the Efferent synthesis and decision making. So we are using some afferentation to find optional ways, and we find some action plan which has the best probability of having the action results succeeded given the starting afferentation. And then the afferentation actually starts some action, and then action is first step of the action is accompanied with acceptance of the action results, and then the results are either accepted or not accepted or partially accepted, and then acceptance or not acceptance of the results is assessed with emotions, which provide the input to the corrective Efferent synthesis and decision making, which is forcing us to complete our interaction with the environment with another acceptance of the results, and then we keep going in this loop till the final acceptance of the results is telling us that we have reached our goal, and we have emotions confirming that everything was just fine, and we provide the memorization of the successive chain of the actions in our memory, so we are increasing probability that this sequence of actions will be reused in the future in the similar afferentation. And that's definitely is not just about atomic action execution. We can build complex behavioral schema from the simple loops to complex loop, and that's covered in the idea of multi-level organization of movements according to Bernstein. So Bernstein investigated the multi-level organization of movements. So the level organization of movements B is body ownership. The moments of the level C of the special field are primary or clearly defined target nature, where they lead to from somewhere to somewhere for some reason, and leading motif at the level of actions D is not an object in itself like a geometric form, but the semantic side of actions with an object. So we are going from higher level to lower level, and these levels can be defined through the chain of actions and the results that they can achieve. We can introduce the concept of a probabilistic goal result of actions so that they can be formed automatically during the learning process. Goal result increases the likelihood of achieving the final result. The goal result has the branching property. If a certain goal result is achieved in the course of chain of actions, then further chain of actions can be developed differently in accordance with the hierarchy of goal results. When the goal is reached, the result should be fixed by a set of signs, fixing completeness of the chain of actions and the possibility of moving to the next chain of actions. Achievement of the goal result is supported by a motion, which captures an increase of the probability of achieving the final goal. Achieving these goal results can be considered as automatic formation of functional subsystems that achieve these goal results. Let's have a bit clarified the concept of the task, given what we have said about the domain model. So as I mentioned, the domain model is a real model of the external world. So it's not a model created by us in some software design that we put into the agent. That's rather image of the world, image or domain or model of the world learned by an agent as a result of the detection of the maximally specific rules during the interaction with the outer world and having them learned in the internal circuits of the brain of the alive being or artificial brain of a system that of the AGI system that we are creating. A goal request is a need to be satisfied, indicated by the predicate P0. The task solution or solution for the task is the object, the situation perceived by the totality of afferent stimuli A, on which the predicate P0 is true, or we have the need satisfied, which is the criterion of the task solution. There may be several solutions such satisfying the criteria, and the choice of a particular solution is carried out by switching function of emotions. Decision-making process is carried out by choosing a particular action plan, taking into account the probabilistic forecast and the maximum emotional reaction for the corresponding action plan, which is formed based on the basis of the existing experience and available maximally specific rules, which predict the achievement of a goal according to the model of the external world, including the object achievement, situation A, making the predicate P0 true. Then hierarchical planning of the goal achievement using probabilistic goal results and available maximally specific rules. And finally, semantic modeling predicting the goal achievement using probabilistic inference, finding the maximally specific rules within the existing knowledge about the domain model. And the particular action plan converts the result goal, converts the request goal into particular request, into specific or particular request goal, given the way of the desired object A, finding together it with the totality of the sub-request goals and the goal results, acceptor of the results of actions, where the acceptor of the results of actions is actually acceptor of the entire hierarchy of goals and sub-goals acceptance. So that's kind of the cognitive model, which represents or cognitive architecture, which covers all the items that we, all ideas that we discussed before. So we have the Efferent Synthesis, which has a request goal and the situation description in terms of the domain model of an environment. Then it provides the input to the decision making, which can further involve creation of the sub-goals and then applying the same schema to each of these sub-goals hierarchically. Then there is a feedback from the environment, and then there are actions that can be executed if there is a final sub-goal and there is no further sub-goal branching. And at the same time, when the actions of a goal or a sub-goals are directed towards the environment with this black arrow, there is a forecast for each of the sub-goals and for the entire chain of the actions represented by the tree of sub-goals. And this expectation or forecast is recorded for a moment in the acceptor or action results, which is waiting for the result from the environment. and the environment is responding with this black arrow based on our actions towards the environment, and we do assessment of the results, and we do acceptance of the action result, and then the result is either accepted or not, and then the result of the result acceptance is changing the situation, and then we are getting back to another situation, or if nothing has to be done, we just stop at this time and start with some another motivational afferentation to execute some another goals. Now let's have overview of some results that we have got. So one example is modeling of the animate. So that's an artificial being that can operate in moderately complex environment, which is not that complex at all. However, there is one important complication in the environment. So there is a food, and the goal of an agent, of this agent, to eat as much food as possible. The problem that this guy has is that it can't consume the food without of having the pills eaten before the food is taken. So let's assume that the food is red, but if it eats the red food, then there is no use. So before eating the food, the agent needs to eat the blue tablet or blue pill. And then if the pill is eaten before the food, then the food can be consumed or digested. So the goal of the agent is not only to learn about the navigation, but also to learn that it needs always to eat one pill before eating one piece of the food. And of course, the eating and moving and turning and looking around are all the elements of the ontology in the world or belief system of this agent, and the probabilistic inference and semantic modeling of the agent learning this behavioral schema is written in the language which is actually representing the activity of this agent. So here is the example. So the world of the agent is, or model of the world of an agent is that it just has center of the world in the middle, and 1, 2, 3, 4, 5, 6, 7, 8 cells around, and each of the cells around may have either nothing or a pill or a food. And so the agent can turn, it can take what's in front of the agent, and that's the world that it has to operate with, and it can learn. It can learn, and our experiments show that using semantic inference, which is rendered with the blue line, performs the best compared to the other approaches. So here is the result when there is no need. So that's the simplified actually chart. So that chart says, renders the case when there is no need to find a pill and eat the pill before eating the food. So eating the food can be done without of the pills. And in this case, if we use random walk algorithm, it's at the bottom. It doesn't work. If we use QLOOKUP table algorithm, it works, but not that good. If we use Q-neural network algorithm, it works, but it reaches the maximum possible level of food consumption quite slow. But if we use semantic inference, then the maximum capability of eating the food is reaching quite quickly. But if we complicate the world of the agent with the need to eat the pills before eating the food, then only the semantic inference, which is dark blue, is working, and all other random walk, QLOOKUP table, and Q-neural network, nothing else is not working. So these algorithms make it impossible for the agent to learn that the pills have to be eaten before consuming the food. And that's described in the work published by Evgenii Vityaev. Here are the references. Some of them are in English and some of them are in Russian. And here is the example. So I have promised that we are going to show how the neural model of a single neuron can be used to create some artificial life in virtual environments. So what we have done the model of the skeleton and the muscles and the neuron connections of a C. elegans nematode worm from the virtual worm project. So this simple animal has about few hundred neurons. And what we have done, we have put the described model of a neuron into each of the neurons of this animal. And we put the animal into the virtual environment, and we have placed some gradient in the virtual environment. So the goal of the agent is to crawl or move. So it doesn't know how to crawl so far. It just needs to move towards the gradient because there is a food expected to be at the destination of the increased gradient. So the agent starts sorry, not an agent, the worm starts moving spontaneously, and it uses the design that have been discussed. And eventually, we can see that the motions of the worm are getting more and more natural and more resembling the natural movements of this worm as obtained, as observed in the real environment. And eventually we can see that it really learned how to crawl, and it starts crawling towards the food. And we hope it will find something tasty. But let us now go to another example. And another example is where we can actually benefit of having the
Edvotech instructional videos.
Oops, one
the
second.
Effects of alcohol on.
Okay, so what we are trying to do here, we are trying to have benefit of the knowledge of an agent stored in explainable representation. So here we have actual use of the word semantic, because the semantic model is not only relying on the underlying semantics of the real world, and semantics of this world is also pretty simple. There is a ground, there is a possibility to move in any direction of the on the ground. There are other species like other peers in the environment, so you shouldn't be crashing into the neighbors moving around yourself. And there is a food, and you should be able to consume the food, and you should be able to consume the food in a situation when the other agents are trying to consume the food. What is important here, that the agents not only can learn, they can also communicate with each other. So when the agent learns something, it can also tell explicitly tell what they have learned so far to another agent. And we have found that when the agent can share the knowledge that they have learned in terms of communicating the elements of the semantic schema that they learn, they can cooperatively learn to consume the food faster. So all mice together here can eat more food in a given period of time than if single mice were alone. So it would take more time for single mouse to learn, and multiple mice learn faster if they cooperate. So let me go back to the presentation. And another benefit of applying the design and mathematical model that we are presenting is to make what we call explainable or interpretable deep learning. And the idea of making the deep learning interpretable or explainable is that we need to redefine deep learning in terms of not just using multiple layers of a neural network, for example, but having some natural levels or natural hierarchies actually supported or supported by the real properties of the environments, or corresponding to real layers or meaningful layers of the natural environments. So that's actually grounded of the works of Gibson about the ecological theory of perception, which says the world is hierarchically structured. Small elements are contained in larger ones. Therefore, I introduce a special term for it, embeddedness. In any part of the Earth's surface, in fact, the same elements are found. The size of grains of sand wherever they meet is always about the same. Grass stems are also more or less the same everywhere. The same can be said about stones, bunches of grass, bushes, etc. And although their repeatability is devoid of metric regularity, they still have stochastic regularity. That is, they are regular in the probabilistic sense. And here we come to the natural concepts in cognitive sciences. In the works of Eleanor Roche, the principles of categorization of natural categories are formulated as follows. The structure of the perceived world. The perceived world is not an unstructured set of equally likely properties. On the contrary, the objects of the perceived world have a highly correlated structure. Combinations of what we perceive as attributes of real objects do not occur evenly. Some pairs, triples, likely enough. Others are rare. Others do not occur logically or empirically. Basic objects are information-rich bundles of observable and functional properties that form a natural discontinuity that creates categorization. Categories can be considered in terms of their pure cases. In the perceiver pays, and if the perceiver pays attention to the correlation structure of perceived attributes. By category prototypes, we generally mean pure cases of category membership. In the future, the theory of natural concepts by Eleanor Roche was called the prototype theory of categorization, or prototype theory. Further research revealed that models based on attributes, similarities, and prototypes are not enough to describe classes. It is necessary to consider causal and ontological knowledge related to class objects. For one example, people not only know that birds have wings, that they can fly and make nests in trees, but also that birds make nests in trees because they can fly, and they fly because they have wings. So the properties, the functional behaviors, the shapes, the colors, the capabilities of the objects, and any events that we are experiencing in our life are connected with different perspectives. And we can apply causal models mutually taking all these features all together. Given these studies, Bob Rechter put forward the causal model theory, in which the relationship of an object to a category is no longer based on a variety of features and proximity by features, but on the basis of the similarity of the causative mechanisms connecting all these features together. To describe causal models, Bob Rechter used a sweep of causal models using Bayesian networks. However, Bayesian networks do not support cycles, and therefore cannot model cyclic causal relationships. What we propose in our work is a new mathematical apparatus, probabilistic generalization of the formal concepts for formalization of the natural concepts, based on the formalization of cyclic causal relationships. During the perception of natural objects, these causal relationships become closer to themselves, forming a certain resonance or cyclic causal relationships, which gives causal models. In terms, by the way, you can think of it in terms of Hopfield networks and attractors in the Hopfield networks. So you can think, if you describe particular world or particular object in terms of Hopfield network, then given the stimuli in the inputs of this network corresponding to appearance of one specific objects, what you get in a Hopfield network is kind of attractor or a stable equilibrium point, which is exactly the resonance of cyclic causal relationships that we are describing in this work, but not from perspective of the Hopfield neural networks, but from perspective of the semantic modeling and semantic inference. Another perspective how you can look into the same problem is from the concept analysis, formal concept analysis paradigm. So I think some of us are familiar with the formal concept analysis idea, where you can define context of any domain in terms of a matrix, where you have the objects on one side of the matrix and the features of the objects on the other side of matrix, and you can identify the clusters of the objects sharing the same features. So let's and the formal concept in the context of this approach is a set of pairs of the objects and features that are having the same properties. Like, for example, we have a finch and the eagle, and both finch and the eagle are flying, and both finch and the eagle are birds. So we can take flying bird, finch, and eagle all together, and that's a formal concept identified by properties flying and the bird, and proper names finch and eagle. And what we do in our work, we are trying to make probabilistic generalization of formal concepts. Mill wrote that natural groups are determined by features. However, this takes into account not only the features that are certainly common to all objects included in the group, but the totality of these features, of which all occur in most of the objects, and majority in all. Stages of probabilistic generalization of formal concepts are the following. First, define formal concepts as fixed points of implications, like we discussed in the previous slide about the causal self-predicting features and properties. Then second stage is about defining implications, where when we replace the implications by the more specific causal relationships. Then we define probabilistic formal concepts as fixed points of maximally specific causal relationships. And then we prove that these fixed points are logically consistent and define natural concepts as probabilistic formal concepts. And then if we do that, we can find a way to come down to probabilistically explainable deep learning designs, where the stochastic regularity and secondary features are also described by probabilistic formal concepts. So the hierarchy of probabilistic formal concepts can be found as follows: automatically detecting hierarchy of secondary characteristics, forming classes of properties as fixed points, explainable accurately and consistently, and have it all transparent and explainable. Here is one example of what we can do about the explainable visual pattern recognition. Let's create a bunch of letters from 0 to 9, and having some of them redundant, like having some of them corrupted, like we can have different versions of 6 here, and we have 2 different versions of 9 here, and they are corrupted in different ways. And let's digitize them on the matrix 4 to 6 cells, and let's have different properties that can appear in each of these cells. And then let's try to find causal relationships between these different features. So like have, for example, for 0, having the line on the left is predicting the line on the right. And for 1, having the line on the right, predicting that there will be no line on the left. And what we can do, we can have all possible mutual predictions of every feature or every combination of different features in respect to other features, and can describe any letter, no matter what are the distorted properties of a letter, as a fixed point describing involving all possible predictions between different features or regularities that are describing particular letter. And we have found that this provides reasonable accuracy and explainability for the recognition of all these distorted letters. Another way where the explainable and interpretable semantic inference, like we are presenting, can be used is data mining. And data mining, in terms of task-driven approach, can make knowledge discovery or data mining on model data more practical. The task concept includes the subject domain and knowledge about the subject domain, presented in the form of model. And then we can consider the problem of inductive inference of knowledge on the data of the model using data mining methods. We can extract from the properties, characteristics, and the attributes of data only the knowledge that is interpreted in the domain ontology. By themselves, the numerical values of the quantities do not contain any knowledge. The knowledge about quantities contained in numerical values plus interpretation. 5 meters, 5 liters, 5 kilograms. And when we deal with the data, we need to account that it is defined by its scales or different empirical systems where one part of the empirical system is the values describing the quantity, set of values describing the quantity, and another part is set of relationships and operations in respect to these values interpreted within given domain ontology. And there are known different sorts of scales, like scale of names, where we can apply only equals and semi-equals operations. Order scale, where we can apply equals, greater or less interval scale, scale of relationships, and so forth. And each of the scales are determined up to permissible scale transformations. And if we apply the data mining to historical data, then we find that knowledge discovered by data mining and machine learning methods is expressed by their own ontology and not by ontology of the subject domain. That means if you find any regularity that you find is raw historical data, then you may find that the regularities are identified by the models that are built into the specific parameters of the neural network or machine learning algorithm that you use, or they may be driven by the parameters that you choose during the hyperparameter learning or hyperparameter tuning up, and then you may apply a set of hyperparameters that can make the implicit domain model of the machine learning algorithm close to the domain model of the data implied by the data, but that's still be not the natural ontology of the data on itself. So data mining and machine learning methods ontology can be applied. So a priori hypothesis classes that the method tests and data types that the method works with can be incorporated into the data mining and machine learning methods. To obtain knowledge by to obtain the knowledge, it is necessary that the method ontology would be interpretable in the subject domain ontology. So we need that the data types of the method must be interpretable in terms of the domain ontology, and a priori classes of hypotheses also must be interpretable in the domain ontology. The method should use only mathematical and relations and operations interpretable in the domain ontology. If conditions 1 and 2 are not fulfilled, then the method will not be invariant with respect to the choice of units of measurements and permissible scale transformations, and most machine learning methods won't be invariant. Ontological approach to extracting subject domain knowledge assumes that we can determine data ontology using subject domain ontology and scale of quantities. Then we can present data in the domain ontology as part of a domain model. Then we can define an arbitrary hypothesis class of interest to us, which should be specified by an expert in the subject domain to which this knowledge is needed. And then we can discover the knowledge by testing hypothesis class H on this data, and also discover subject domain theory operating within this domain ontology, all rules with maximum conditional probabilities, and all more specific rules that allows us to make consistent predictions with this subject domain ontology within subject domain theory. And what has been created by Evgenii Vityaev is a discovery system which was developed implementing semantic probabilistic inference that discovers all rule classes starting from the simple non-probabilistic rules L, then maximum specific rules, and finally the scope of all domain knowledge, including all non-specific rules, maximum specific rules, and non-probabilistic rules. And then the domain model in semantic modeling can be enriched with all these rules, given the domain theory and probabilistic knowledge at the same time. That's all is described in the book written by Boris Kovalchuk and Evgenii Vityaev, and also there is another book by Evgenii Vityaev in Russian about extraction of knowledge from the data, computer cognition, and modeling of cognitive processes. And here are just few final examples about how we can apply the semantic modeling and interpretable prediction in respect to prediction of financial forecasting, in respect to S&P 500 index in this example. So what is known from the domain knowledge is that the week of days matter, and simply having the numerical series or trend analysis or Fourier analysis based approximations to the numeric data is kind of misleading. So we need to account the real world context, such as days of the week, and we can explain the rules of the changes on the financial markets in terms of changes appearing on particular weeks of the days. And the rules here are actually corresponding to the rules that are created by the experts in the domain, like brokers who actually learn the financial trends, but the rules here are actually found out by the system. So these rules are inferred by the semantic inference process. For example, on the left, the rule is saying if the price is going up on Friday, and then it goes down starting Wednesday, and then it starts going up again on the next Monday, then there is a high probability that will be going up till the next Monday. And that's kind of rule bound to specific days, and then which can be used for predictions. And all the other rules in the columns 2, 3, and 4 are actually representing another prediction structures, and based on the combination of the prediction structures that you find given specific time period, you can actually make more or less reliable predictions for particular periods. Like, for example, if you find that you have two different rules predicting that the price is going up and two different rules predicting that the price is going down, then most likely you shouldn't be relying on this prediction. But if you see four different rules all saying that the price will be going down tomorrow, then you have kind of explainable idea why you should be buying or selling your stocks starting the next day. And that corresponds to what is actually used in the financial prediction by the name of the technical analysis figures. So the technical analysis figures used by the brokers are explicitly figures that are saying that at some point something is above something, and then it's below something, and then it's above something. So you can describe the figures of the technical analysis using the logical conditions bound to the levels of the price at the close and open price. And then that's a kind of symbolic representation of the knowledge, and that kind of symbolic symbolic rules can be found with the discovery system using the formalism described in the previous 1.5 hours, and these rules are probabilistic as well. So each element of this rule and the rule itself can be given particular probability, and you can look at this figure as a symbol and apply it to the symbol, entire symbol. And if you have multiple symbols, you can consider conditional probabilities of every of these symbols and make your decisions in the end. And another domain where the explainability of the knowledge representation and prediction is important is medical care. So here is the example of the rules for breast cancer diagnosis system prediction. And on the right, you see the accuracy of the cancer diagnosis based on these diagnostic rules. It varies from 92%, 93% to 100%. And the rules are the rules that can be actually verified by the doctor. So it gives prediction in terms of on basis of the diagnostic rules, which are explainable and operates with number of classifications per centimeter and ranges of these classifications and the volume of the classification, and these parameters can be actually communicated to the doctors, and you can actually find different combinations of rules and apply all this analysis in respect to maximally specific rules in respect to given medical cases. So if you are interested about this, you are welcome to write email to Dr. Vityaev, and here is his mail, and here is my email, and we cooperate and work together. So stay in touch with us. And if you are interested more about the discovery system and the works underlying it, there is a web link on the scientific discovery page. And if you are interested about Animat's development, then there is a open source code that can be used for the experiments. Thank you, and we have some little time for questions.
Do we have any questions?
Hi, Anton, thank you very much for a systematic overview. It was very interesting. Although I'd expect more simple practical examples from the tutorial. So it's nice to see that there is an open source implementation. Can you copy paste this link to the chat?
Sure.
Is it only for Animat, are there any examples of using other solutions you described, like semantic programming or modeling using ontologies? So how other examples, how can we describe domain knowledge? How can we specify goals or queries to this engine and so on?
I can answer. Yes, there is some experiments with animats. The last experiment was in animat, which made from 10 from 10 parts in any switches, and in any of this animat, the adaptive system was included, and each of it find some possibility of movement. So some animats was developed, and from practical point of view, it is important that we used a semantic modeling for make a model of of big number of shops. We made an online system which gather checks from 1,000 shops, and these checks is analyzed and in online give a result of shops working, and it made on so-called document modeling, where each document was made a web version, and each parameter of document was interconnected, and there is no a programming of this model. These all connections are made a so-called executable specification of interconnection of all parts of this documents, and it works in rather huge number of checks. Yes.
Well, thanks, but maybe my question was a little bit different. I meant, can you show some examples of the rules and domain knowledge and queries to it as tasks and so on? So are they available for like for experimenting, contributing, and so on?
In experiment with mouses, in the right side of the screen, there was shown a learning process where rules applied was shown, and also how they works, and also reinforcement of these rules also was shown, and all this information may be made available.
Okay, thanks. Maybe I'm misunderstanding something. It sounded like there is a sort of general purpose cognitive architecture or platform or something like that in which you can implement different things, like these experiments you are showing now, animats, financial analysis, problem solving, planning, and so on. So maybe I'm wrong. So maybe the right question would be, is such a platform or cognitive architecture which can be used for different purposes, or are there only standalone implementations for different experiments, like this one with mice and another one with financial predictions? Is the question clear?
Yeah. Yes. The link on code. It is open code for functional system, but functional system is rather general, so it may be applied in different tasks.
Okay, thank you. We have a question on chat. Maybe since I'm talking, I can read it. At what rate do you foresee general AI taking off?
What question? I don't understand.
Alexei, I mean, how soon should we see the artificial general intelligence to appear?
You can read it on chat. Maybe Anton, you can moderate the further discussion.
Let me go to the chat. At what rate do you foresee general intelligence? I'm not sure what you mean by rate. So if the question is about, so I see the question, then how soon can we see the general AI to appear? So that's my interpretation of the question.
Yeah, my also.
Evgeny, can you answer? When can we see the artificial general intelligence to appear?
General artificial intelligence, in this presentation, we wanted to show that this is some approach to general artificial intelligence in such a way that a particular part of this approach can model a cognitive process. But in general, this description may be considered as a rather general way of executable specifications, in such a way that if we can to specify a task, after that we can achieve a result using a specific constructive model.
Well, I would take a step to answer this from another perspective. So if we consider narrow artificial general intelligence, then I think that we may see artificial general intelligence for specific domains appearing within 10 years. So like if we want to create the general navigational intelligence for the self-driving vehicles, for city navigation, it might be available in 10 years, for example. Or if we want to create some narrow navigation, narrow artificial intelligence for the medical domain, for medical diagnostics, then also we may because this domain is well formalized and formal what we call ontology models are available, and also within 10 years I think we can get progress with building the narrow general applications, narrow artificially general intelligent applications for medical care within 10 years. But about having the artificial general intelligence that is comparable to the intelligence of humans, I would be careful making predictions because we still don't completely understand the nature of the human intelligence. So I would be very careful making predictions about the human level intelligence. Well, so then another question that we have on the from the YouTube is, doesn't using money as a reward function get in the way of living AI? Yes, of course. So if you are, for example, if you are creating narrow artificial general intelligence for doing financial predictions using the applying the capability of artificial intelligence to discover figures of technical analysis and selling and buying stocks, then obviously the money earned by this automated trading is a essential reward function, and we can build autonomous AI living on selling and buying stocks online. So then another question: when will your reputation model be able to run actually on AGI platform? Okay, so that's the question is not related to the given talk. It's about the reputation system. And by the way, I will tell a few words about the reputation system using my keynote on the last day. And right now, you can use our reputation model on any platform and not necessarily AGI. Right now, there are two implementations of the reputation model. One is in AI agents Java code, and another is a Python implementation, and both have a web service API, and you can use it either as a library or as a standalone service to run your code or to run any AGI platform code. Of course, there may be some bugs, there might be some improvements, but at a prototype or beta version, two versions of the reputation model can be used. Well, I think we have run out of our time, team.
Yes, we
I think
have.
there is a last question then. Can you build human individual config files for the generic human model to derive specific individual person models? Well, theoretically, yes. As soon as you understand the nature of the human behavior, the human soul, you can create this model in terms of the design that we have presented today. So all what you need, you just need to build complete subject domain for the human soul and human behavior and human all aspects of the human living. And once you have, you can have this model and you have enough computational resources to run probabilistic semantic inference on within this scope of the data supporting this ontology, you can run the model. When you can build this actually model is interesting question. I would be very careful making this as expectations, but I think that if the humans survive on this planet, then within 100 years, it will be possible.
There is one more interesting question. How can we ensure we are including all data to ensure probability calculations are accurate? Of course, we not use only probability. We also use a special statistical criteria for example, for semantic inference. And we use a particular Fisher exact criteria for checking some inequalities in probability. So we of course use some statistical criteria.
Well, from my perspective, I would add, so that's a question about general experience-based behavior. So even for human, you are not always sure that you have used all the data enough to make your probabilistic calculations made by human brain accurate. So you are just having probabilistic models, and as long as your expectations are met, So as long as your predictions making it possible for you to perform and to reach your goals, you can think that you have enough data. But then something changes and you have some novel experience, and you can figure out, and you suddenly figure out that all your models of the world were wrong, or they were wrong in particular case, and you need to find more data to fix your models. So that stays true for the humans and artificial beings. So you never know everything.
One more question.
Yes,
Is it possible to get this presentation for offline reading? I think that this talk will be read, and also a special talk on this presentation was made in Russia, and both these talks will be available, I think.
Yes, I will add. So let me just try to make sure. So here are, so you can see the two emails here. So yeah, I believe that the presentations and videos will be available on the conference site. But if you miss the presentation or the video, you just send email to either myself, or the Evgenii Vityaev, and we will send you links to the slides and to the English version of this talk and to the Russian version of this talk. And by the way, well, yeah, so that's.
Okay, I think we're due for a break. And then in half an hour, we will reconvene. Thank you very much, Anton. That was really very interesting. I'm sure that everybody listening to this found that to be fascinating. And if we can obviously have the presentation to delve into, and then any further questions, by all means, we'll fire to you. And thank you very much.
Okay, thank you everyone, and
Thank you
for attention and for the questions. Bye.